Hello, everyone.
Good morning.
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 Hello. Morning.
Yeah, we have Jeff said there's a conflicting meeting for IEEE. So so I believe we will have probably a little bit less people today, but luckily everything is recorded, so people will be able to catch up by the video replay. So let's give people maybe 1 or 2 minutes more, and then we'll give the stage to Raymond. James is helping me to organizing the breakfast gathering on Thursday. Hi, James.
Hey guys. Yeah, I'm just trying to finalize the contract details with this place that's close to the event. I'll throw the website into the chat. It's called The Grove. It looks like a pretty decent place for breakfast, and they have like a room that's like a mezzanine upstairs room. They can seat 20 people or so, which is nice. So we'll hopefully get that. I'm trying to close on it today and waiting for their manager to arrive at work and call me back.
Awesome. Thanks, James. So yeah, so like Jim said, we'll send out more details about the OFC gathering on Thursday, April 3rd morning. Hopefully we'll be able to see most of you. All right, I think let's, Raymond, do you want to get started?
So let me share my screen.
Thank you.
Let's see. So let me make sure I'm sharing the right window. And please let me know when you can see it.
Yep, it's popping up.
Okay, so my name is Raymond Law and I work for Lowe's. And this is actually a summary of what we being the Lowe's team was able to take away from the 400G workshop the day before DesignCon. So it's like roughly 2 months ago, not quite. So just give a little bit of background, right? So Lowe's is actually not a optical solution provider. We are actually in the cable connector space. So we deal with copper. But as the speed keep going, the writing is on the wall, it is everywhere. It's just a matter of time. If we keep increasing the data rate, optical is going to be more and more prevalent. So as a company, we are looking forward to where do we need to start really paying attention to optical, and that's why I'm here in this particular work group. And now with that, the focus of the 400G workshop is actually similar to what I just said. So it is looking at the potential enabling path and challenges to go from right now, we are kind of starting to wrap up Gen 7, which is 128, and then looking forward to 224, UA link, and then 400. But the focus really is on the high-level interconnect architecture and trying to extend the reach of copper. Now, I think most people would agree that copper is still cheaper, and but to be honest, by the time we get to 400G, if we need to use multiple repeater, and if there's some new technology need to be enabled, I really don't know how much of those perceived advantage of copper is going to stay. So, but anyway. So there are 5 presentations being summarized in this little slide deck. So it's Meta, Synopsys, Alpha Wave Semi, and Amphenol, and TE. So 5 of them. And the first three, Mater is a system company, right? But Synopsys and AlphaWave, they do IP design. So their perspective actually is quite interesting to me. Okay. All right. Any questions over? Okay. All right. So the format of my summary is going to be a few slides for each company, and I'll start with a main point, and it's my summary. So if any of you happens to have seen the slide that one may actually be there during the presentation, and you have some other insight, please do share. Okay. So Mater, I think they come out, the first point that they make is they want to connect everything, all the accelerator, all the switches, and that's a lot of connections. And the next slide go into it a little bit. And of course, they need a lot of bandwidth. That I think we all know. And of course, they want to keep using copper if possible. There are a couple things that they mentioned that caught my attention in their presentation. Those are related to CPC, which is co-packaged copper, and it's co-packaged connector, copper connector to backplane or to front panel pluggable. And this is an optical transition from a internal copper cable going to outside to optical. Okay. So let's go look at the top level, very, very high level description. So this is actually a screen capture that I got from their presentation, and this look awfully like a NVIDIA GB200, the NVL76, and the 32 actually looks just like this. To be honest, it's just fewer tray, and it looks like they have the compute tray on the top and at the bottom, CPU with GPU, and in the middle is all the switches. Now, to do the scale up network here, if we want to connect from the top or the bottom to the middle, we need something more than 1 meter. It really depends on how exactly where the connector are from the top, I mean on the tray, along the tray, and the switch. So I grabbed this one from the OPC PCIe extended connectivity white paper. And they have actually multiple drawing like this to illustrate the length requirement. For this one, it is showing from the top or the bottom in the middle of the tray to the middle of the rack, middle of the tray. And they estimated 2 meters. So that kind of gel with my estimate here. Needs to be 1 meter, maybe up to 2 meters. Okay. Now, let's see. Now, scale out network that can connect to nearby racks. Now, I think the current assumption is by 224, we are probably looking at active cable as a potential enabler. And it seems like NVIDIA is already doing it. Now, exactly how long, that's debatable. So, but I say nearby racks probably is just maybe 1 up to 2 over. If that's the case, we are talking about somewhere between 5 to 7 meters. So, okay, any question? All right. Okay. Okay, so this is the current Meta 200G topologies. Just 3 screen capture here. That's how they uh, um, illustrate the scale out. It looks like Meta use NPC. This is near package connector. There's a copper connector. It goes from the ASIC through the interposer and the substrate, some PCB route, probably pretty short, and then send out through internal cable to pluggable transceiver. And they label this as optical cable. So I suspect their transition is in this plug and receptacle area. Likely is on the cable, but I do not know for sure. For scale up, it's very similar. It's still MPC connector, internal cable to a backplane I/O connector, and then it's just backplane cable. Now, on the other side is just symmetric. It's just I/O connector, internal cable, MPC. So that's good. Now, but we're still not going to 400G yet. But they did mention one of the challenge that they can foresee is the MPC will become very challenging. The reason being the loss along the package route is going to be pretty bad by 400G. So what they have here is just a cartoon of how the silicon go on top of their interposer and then go through a very thick substrate. This is a very simple illustration of how the package would look like in terms of routing, but it's realistic. A well-designed package route really shouldn't have too much. It should just have one main route, and then we'll just veer down as much as possible, as strict as possible. So, and of course, with today's server silicon, or I shouldn't say one silicon, it can be just a whole ASIC. There can be multiple chiplet with the size of the package. This main route can be quite long. So they are pointing this out, the loss of the package. So their solution is move the MPC as near package to on top of the package. Use CPC full package. So the topology here actually is almost the same as the previous page. It's just from near the package, put it on top. And it's still the flyover cable, Blackpink I/O connector cable, and then go over like this. The interesting thing to me is they didn't mention anything about active copper cable here. There, because by 400G, even if we do CPC and just half a meter of passive flyover cable, the Blackpink probably, with 2 meter in mind, a passive cable probably won't do. You probably need something active. They didn't mention it, but it's just in my mind. And for the optical transition over here, pluggable transceiver, same idea. But they added something kind of interesting here. They say on-board optics, OBO. So they suffer the loss on the package, but then very close to the package, they turn it into optics and go out. Now, exactly how this go out is unclear. Unlike at the edge of the motherboard or the tray, that you can just plug something and go out. Over here, how the optical cable is going to sneak through some kind of hole and come onto the package, I mean the PCB. This may be an area of opportunity, but it's unclear how it can be done. And one
That's
thing that
actually
is
should be pretty easy, right? That's just terminated with a connector on the board, on the front panel or back panel.
front panel or back panel, you mean
This is well established, right? Just basically either connectorized or even backplane, but optically.
Oh, okay. Okay. So I can
It basically looks like a patch panel, Raymond, but from the outside, a cable plugs in just like into a transceiver.
so you are saying that if this is the edge, let's say this is the edge. Oh, this is very thick. Let's say this is the edge of the tray or the rack. So there's actually a optical cable just come in through a hole and plug in like this.
Not through a hole. The pink thing becomes like a patch panel. You put a fiber
Patch
adapter
panel.
to
Oh,
one connector each side.
so it looks kind of like a Blackpink copper connector kind of thing.
Yeah, I think
Something.
so. Yeah, like yeah.
Okay. Okay. Thank you. Thank you. And something that Mater did not mention, which actually exists because I have seen Broadcom talk about is CPO co-packaged optics. If they are willing to do something like this, why not just put this on the package? Just CPO all the way out. I think Broadcom is trying to do that already. So, but it's something to think about. And one last point, and you are going to keep seeing this over and over. in my slide deck because other company also mentioned it. Meta just touched on it, but many other company mentioned that the PAM4 is going to be a little dicey by the time we get to 400G. It's likely that we'll need something more like PAM6 or some other modulation scheme. So they'll keep coming. So any question? Cool. All right. So Synopsys. Now Synopsys is an IP company, so their focus is more on what they see from the circuit design side. And they come out just saying that, and I think there's nothing new. Everybody knows that with the AI push, the industry just keep asking them for higher performance IP, and they need to come fast. Basically, they keep saying that the time to market, the request for time to market is very, very high. And they don't think copper can support 400G with PAM4. It seems like they are more promoting the PAM6 with some acceptable increase in complexity, area, and power. They say that beyond PAM6, they can also do PAM8. Apparently, they looked at it and bidirectional PAM4. But they are complicated enough that it will require them to change their PHY design, and the time to market may not be acceptable. So this is the high level main. And I also capture some cartoon drawing. That is the things that they looked at. And this is just half of the whole system, clearly. They look at something that is not retime. So this is very similar to what Meta has just shown from the ASIC directly to some form of connector, or flyover cable with a near package connector, or just CPC flyover to a connector. Now, what they add, which is something that Meta did not add, is retimer. They specifically call out retimer. I don't know if a redriver will be able to work. If a redriver can work, then people would usually use a redriver just because it's cheaper. But it's the same idea. So you need to add an active component. They put it on the motherboard. And again, I think there may be a possibility to put it on the cable over here. Okay. But they point this out actually is from their perspective that with different topology and architecture, all these can affect the PHY design. And being Synopsys, probably one of the biggest IP provider out there, they have a very large samples of reference channel. So it looks like they have some reference channel that is relatively short or low loss, all the way to something that is very high loss. And they put a line here that probably around 53 gigahertz. So it really depends on the modulation scheme. This is near the Nyquist. So the existing 224, they say it took a sharp decline above 60 gigahertz. This is actually, I think I copied it out more or less exactly. But being an electrical guy, when I look at it, I think it really depends on which channel you're looking at. Some may be a little bit higher bandwidth. This one looks very extreme, to be honest. So whatever. But their main point is the channel composition need to be improved. Okay, they want to improve the channel loss and by loss it's probably not just insertion loss. It's a whole lot of things. There's a return loss and crosstalk and the whole nine yards. But they also, of course, mention reducing the baud rate. At least don't increase it too much, or to a point that they make life too difficult. So, now, interestingly, they plot out the line loss versus the reference channel number. So again, so from something very low loss to something that is very high loss. And they call out PAM6 has a fixed signal to noise ratio penalty compared to PAM4. But as the channel loss increases, they point out that the advantage in terms of insertion loss, PAM6 keep increasing. So for I would say in the server market, when a lot of the time we look at long and lossy end-to-end channel, I think this is Synopsys' way to say that PAM6 is looking more attractive than PAM4. But of course, they also say that Synopsys can do both. They can, doesn't really matter. It really depends on the direction from the industry. All right. So this is a very interesting table, and to be honest, I don't understand half of it. It goes into, they talk about different modulation scheme with different coloring scheme. And then there's some other information here, pretty easy to understand, like the baud rate, the nitrous, number of level. And the consideration here, when I say I don't understand half of it, is because of the comment here. Because they talk about, let's say, the cross 32, I don't know what this is. PR PAM4, I also don't know what this is. But there are a couple key takeaways. They already mentioned PAM4 is going to be rather difficult, even though there's backward compatibility and aligned with optics. But if they try to do something that is other than PAM6, like PAM8, there's really high signal to noise ratio penalty. We actually know that. But the bidirectional PAM4, they will need some form of hybrid or echo canceller. From a circuit perspective, I don't know what this is. But they can keep the same I/O count, so that helps. Anyway, so they Synopsys specifically call out these two rows and say that they are very difficult to meet the time to market need.
Yeah,
Okay.
just a quick comment here is a lot of the assumptions base uses doing whatever you've been doing, right? Like PCB material has been same, and I think at a certain point you will have to say what can make it work other than what it doesn't work. Because if you look at media, I mean, they're really like using very expensive dielectric material for backplanes. I mean, you had to actually look at what actually make it work. Otherwise, we just keep talking about what doesn't work. I mean, there's just so many things doesn't work.
Yeah. So when we go to some later, especially the last two, the presentation from Amphenol and TE, they mention something that they are doing, but they are not disclosing precisely what they are doing. But yeah, there's some area that need improvement and is being pointed out and is not totally out of reach. Yeah.
That's okay. These vendors, they will disclose over time. They're just not, disclosing the public yet.
Right, of course. Okay. All right, so let's go take a look at Alpha Wave. So Alpha Wave is also an IP provider, and they are not as big as Synopsys. But of course, they are also pointing out more or less the same thing. They need further improvement of the electrical interconnect. Yeah, of course. But interestingly, Alpha Wave thinks that PAM4 is possible. I think I know why in some of the later slides. When we get there, I'll point it out. And they say they need more refined channel. So let's take a look. So the next slide, this is I keep it. I capture it basically for internal to Lowe's, some explanation about how complicated the 30 design is. And I suppose most people in this call have some idea about what is being shown here. I'm not going to dwell on it, but at least the one key point here, Alpha Wave is pointing out is with the current 30 architecture heavily using DSP technique on what they call the digital backend, which include the FFE, both the RX and the TX, and the slicer, the DFE, the MLSD, all these things. Because it's digital, it actually benefit with technology advancement, so the silicon technology. But the front end, the analog side of things, is it doesn't scale as fast as the digital backend. By scale, I mean as the silicon technology improve, the analog front end doesn't improve as fast or as easily. Something like the termination, the parasitic capacitance, their use of inductance to try to equalize it out, and all those kind of things. Actually, those are more or less pure analog technique, and the digital improvement may or may not help. But
Yeah,
that,
just
that's
be clear when you say technology really is advancing the CMOS node, right? From
Yeah.
5 nanometer to 3, 3 to 2.
Yeah. Mhm.
Yeah, this doesn't help on the analog side.
Yeah, the analog front end side. Yep. Okay. All right. So if we keep moving, then
Wait,
here is the thing.
Raymond, you said this was an explanation for why you think PAM4 is possible?
No, this is actually is just the main point that they were saying that the high-speed PHY become more and more complicated.
Oh,
Because I actually many years ago I actually do circuit design, and back then the RX is actually a lot easier. We didn't have DFE and we didn't have FFE, right? We have a CTLE with a VGA. We don't need to put in an inductor to try to equalize out the parasitic cap and those kind of things. So over time it's getting a lot more complicated. So, and it's just getting worse.
Yeah, I think the Mike Lee from Intel are the main advocate for PAM4, right? He's been saying PAM4 is possible for many times.
Yeah.
Yeah. I think at the
Yeah,
end it's about engineering constraint. And if you're not stating the constraint, that conclusion is very tenuous. I think you need to know if you really want to stretch like several meters of copper, yes, not possible. If you bad PCB, no, not possible. But I don't think PAM4 in itself is not possible.
Yeah. Okay. All right. So let's look at the channel that Alpha Wave put in their slide. This actually is a pretty busy plot here. So the first thing that struck me when I saw the presentation is they use a very simple topology. It is CPC on package, co-package connector here, flyover cable, 33 gauge, which is pretty thin, so it's somewhat lossy, but it's very short, only 0.5 meter long. So this channel, just looking at it, is very simplistic, and it avoid channel complexity. That's like a front panel pluggable or any of the PCB route. So the channel look clean, relatively clean, and let me try to explain that. So if you look at just let me pull your attention to all these resonance deep here. So there are actually 3 set of different data. So one set here, if you could follow my cursor, 1, 2, and 3. And this is the roll off around 90 gig, and then around 110, and then beyond 120. So the 90 gig here is all this deeper solid color. They call it the current generation channel at different length, 125, 250, 375, and 500. They call it current generation. All these have a pretty solid bandwidth wall right around 90 gigahertz. And then they say the next gen can go all the way to 110. I don't know how they get there, to be honest. And then if they scale the next gen, and it can go all the way to beyond 120. I have given I'm a cable connector guy, I have a lot of question here, but take it as a face value. So this is what they want from a channel perspective. At the end of the day, they would like to be able to at least push to like beyond 100 gigahertz bandwidth from a channel side. And they use two metrics to say that it's going to work or not. So this screen capture has the BER on the left-hand side and the COM number on the right-hand side. So if we look at the color label here, so the two blue, the deeper and the lighter blue, these are the current gen channel. By the way, all of them are 0.5 meter long. The cable are 0.5 meter long. And the deeper color doesn't have the MLSD, which is the maximum likelihood sequence detection. So this is kind of like a deep red and orange. This is with the next gen channel, and of course the scale next gen. So this is where they think that with PAM4, if you have like the next gen channel or the next gen with the MLSD, the COM number looks okay, touching 4 dB, and the BER here, we can argue that the next gen without the MLSD is not good enough. It's not even touching the 1E-5, but it seems like the MLSD is going to help a lot and move it all the way to almost 1E-9. So this is probably acceptable. Now, but again, they have some very simplistic channel. So I am not sure if it is just next gen is actually going to be good enough. PAM6 seems to be far more promising. Now, of course, if by some other enabler we can push the channel to the scale next gen, then yeah, we can. PAM4 is okay. It's not out of reach. Now with that, I'm done with alpha wave, but we are already on top of the hour. So Bobby, should I keep going with Amphenol and TE, or should we do it next time?
I think we should probably do it on next time. So yeah, people probably have things to working on. So yes, it's a great presentations from Raymond. Thank you once again, and we'll continue this next week. And if anyone has idea about the white paper we're working on, I think I'll talk to Ryan offline about the possible draft a little bit, and anyone please contact me, and hopefully I'll see you all in the OFC in 2 weeks. Thank you, and we'll see you next week. Yeah,
thank you.
Yeah, thank you very much. Thank you, Raymond.
Thank you very much, Raymond.
Bye-bye.